All right. So let me take a moment and read through the solutions for this most recent homework. I'm going to read only the even, since the odds you should have checked on your own. So starting with 42, I have negative 435 over 106, and then 783 over 106. For 44, we have 261 over 73, and negative 696 over 73. 46 is 61.56 pounds. 48 is 95.22 pounds. And 50 is 99.06 pounds. 95.22. 46, 61.65. All right. Repeats or questions here? Megan? All right. So 50 says a crate weighing 80 pounds is being pulled up a ramp at an angle of elevation of 29 degrees with a force of 130 pounds. The ramp has an angle of elevation of 22. So I have three vectors here. I have a gravity vector, which would be 80 cosine of 270, 80 sine 270, which comes out to just be 0, negative 80. I have a pull vector, which is 130 cosine 29, 130 sine 29. And when we type that into our calculator, we get 113.70 and then 63.03. And then I have my ramp vector, which is going to be 1 cosine 22, 1 sine 22. So when I type that into the calculator, we get 0.927 and then 0.375. Okay? So I have to do two projections and look at their difference. So I'm going to project the pull vector onto the ramp and subtract from that the magnitude of the projection of the gravity vector onto the ramp. Now in each of these cases, the magnitude of the ramp, the vector we're projecting onto, is 1. So in each case, we're projecting onto a unit vector. So we can actually do these using the shortcuts. We can just do P dot R and then G dot R. And I think when we do this, because the gravity is pulling down, we're going to lose that. We take a negative sign along with us if we're just doing the dot product. So instead of subtracting the negative, I'm just going to add, because I think when I do the dot product, this quantity is negative. Pretty sure looking at the numbers, that's what's going to happen. So here I'm going to have 113.7 times 0.9, let's do this, 27 plus 6303 times 0.375 plus, and then the other one is going to be 0 times 0.927 plus negative 80 times 0.375. And when I crunch those numbers, I should get that 9906 that I advertised. Megan, does that feel okay there? Ingrid? So if something has a mass, gravity is going to act on it. If no mass is given, or the mass is 0 or negligible, then there is no gravity vector. Gravity only acts on things that have mass. So for example, like light or sound, these are things that have no mass to them. Gravity doesn't affect them unless you're really looking relativistically at like quantum level. There's some argument that maybe gravity affects light or bends light, but that's like way super high-end like physics stuff that is way beyond the scope of anything you talk about in a high school course. Yeah, you're welcome. Lindsay. Okay. 48 says a crate of negligible weight. So when I hear that, I know that there's going to be no gravity vector involved here because the crate doesn't have any mass. Is being pulled up a ramp at an angle of elevation of 53 degrees with a force of 105 pounds. So my pull vector is going to be 105 cosine 53, 105 sine 53. And then it says the ramp is 15 feet long and 8 feet high. So I'm going to use that to define my ramp vector. And now what I'm going to do is I need to calculate the projection of that pull vector onto the ramp. In this case, because r is not a unit vector, I can't do the shortcut. So I actually have to go ahead and do this the kind of the long way. So I need to calculate the magnitude of the projection. I'm going to do the projection by definition. So if I do the dot product, typing that into my calculator, I get 202,494-ish. And then the magnitude squared is going to be 289. And so when I do that, scalar multiplications, I get 10501 and 5605. And then the last step is to do the magnitude. And when I do that in my calculator, I should get the desired result, which is 119 and change. Lindsay, is that okay there? The alternative there, what you could have done instead also is you could have converted this to a unit vector and then used the dot product shortcut. That would be okay to do too if somebody tried doing that. I think that should work. Let's just check real quick. So that would be 1 over the square root of 289 times that stuff. So I would have 15 over 289, comma 8 over 289. And because this is just like an intermediate step, I'm not going to bother to rationalize the denominator here since we're going to do something again with it. So if I call this maybe R1 or something, if I then did pull dot R1, I should get my desired result. So 105 times cosine 53 times 15 divided by 289 plus 105 sine 53 times 8 over 289. Oh, that did not give me the same answer. What happened? Why didn't that work? That should have worked. Huh, maybe that won't work. I would have really thought that would. Let me think on that as to why that's not working. It's not obvious to me right away why that's an issue, but remind me again next time. I'll think about it a little bit later today. I don't want to waste a bunch of time having you guys watch me play around and figure out why something didn't work, or if it's not going to work at all, kind of thing. But you can always do the definition. Okay, Val?
I have a question.
Yeah.
I keep multiplying here on, and I'm just now doing it to 2.
So you did 105 cosine 53 times 15 plus 105 sine 53 times 8?
Yeah. And I keep doing 1,618.7.
This sounds like I have to look at your calculator question later. Yeah, this is a later question, but I don't know, it should work. I just did it on my calculator and got exactly that number. So, I'm not sure, but we can figure it out later there, Meg. Are you in the wrong mode, perhaps? Are you in... You're in degree mode? Oh my goodness, guys. I did 150 cosine when I typed it in instead of 105.
Go ahead and go to the top.
What is this supposed to be? 95? Oh, good. Okay.
105?
No, 95.
Oh, that's the answer.
Yeah. So that's actually really good because you know what happened then? The other one that I showed you guys works just fine. Okay, so Lindsay, returning to our conversation about the potential shortcut, it worked. It's because I typed something into my calculator wrong here. So that number is wrong then as well. That should be like 84. Okay. So Lindsay, I lied. That other unit vector thing worked just fine now that I had actually the right answer at the end. So that's what it was. I was really surprised that it did not work. I was like, I really thought that would work.
See, we worked it out, Mr. Cole.
Good. I'm glad you guys said something.
Yeah.
Wait, is it just 90? Oh, we don't know the exact number.
I mean, it's 95.22 or something. Lindsay, sorry to make a mess out of that.
No.
You're okay though?
Yeah.
You feel satisfied? Okay.
What is like under the square root after 15?
Huh?
Like after 15, 8, like for the R, what was in the red, the square root? 1 over what?
289. That's just 15 squared plus 8 squared. All right, here we go. 46. This will be the last one that I'm going to do. So it says Paul is sledding down a hill with a 20-degree angle of incline. So that's going to be my ramp vector. But here, because it's sledding down instead of getting pulled up, it's going to be negative 20 instead of positive 20. Is that okay, Val?
Yeah.
Okay, that's probably the issue. And then if Paul and the sled weigh a total of 180 pounds, my gravity vector then is 180 cosine 270. 180 sine 270. And then my magnitude of my projection of the gravity onto the ramp is just going to be r dot g, which is going to come out to be just negative 180 times sine of negative 20. And I guess this is 61.56. I did some shortcutting on that dot product there.
Yeah, why should we make it negative?
Because it's going down the hill instead of up the hill. So if the angle of incline is whatever degrees and you're going down the hill, it's like a negative angle because you really want, you have that situation where you really want that angle. 340 is equivalent, yes. So writing the negative 20 or writing it as positive 340 are both the same. They're both coterminal, also perfectly acceptable. Okay? Okay. Moving forward. This is our last two-dimensional topic. But I think this is actually a little bit of an easier or more familiar, let me phrase it that way, of a two-dimensional topic. So a little bit of a notation change that we're going to use here. We're going to introduce another way of writing a vector. The text pages refer to this as IB component form. When I learned this stuff, we just called this a column vector. But all we're doing is saying for vector AB in component form, we can write this as the column vector AB. That's it. Yep. That's the name that we're using in the book pages. I'll call this IB component form. I'll call it a column vector. I'll call it a 1 by 2 matrix. All of those names are equivalent. You could use them all interchangeably. They're all describing the same thing. Okay. And we're introducing this form because this is the most common representation of a vector when we're writing like an equation of a line, which is what we're going to be talking about now. So let's say we want to write the vector equation of the line. So recall back from your Algebra 1 course. What was the equation for a line? I equals mx plus b. In order to write a equation for a line, what information did you need? So what kind of starting information could we give you to do this? There's two situations. You need more than a slope. Okay. Slope and y-intercept. Really, this is, though, more generally, the slope and a point, right? Any point on the line would work. It doesn't have to be specifically the y-intercept, but that's, more generally speaking, any point is fine. What else? What other kind of starting information could we have given you here? Think back to your Algebra 1 class. Wasn't that long ago. What other information could we give you and ask you to write a line from that information? 2 points. Thank you. Okay. So we're going to be using the same sort of information here. But we're going to now kind of do the same process using the language of vectors instead of using the language of points. This doesn't dramatically change the process, but we have to make like some updates to account for the fact that we're using vectors. So my vector line equation we're going to write as r equals r naught plus vt, where this is our point vector. What do you mean? Is that a u? That's a 0. Where r naught is a point vector and v is a slope vector. Is what a plus minus? That is a T. That is the letter T. A lowercase t. I put a curve at the end of it so you can't mistake it as a plus sign. So let's say we want to translate this equation into vector form. What is the slope in this equation?
1/2.
1/2. And remind me, how do we find slope again? No, how do we find it? Other way around, though. The change in y over change in x. So if I wanted to convert this into a vector, what should I put as the x component? So if I'm converting this slope into a vector, what should I write as the vector's x component? 2. And what should I write as its y component? 1.
1.
Do you see why we're doing that? Yeah. Is everybody okay there? Okay. And then what if I wanted a point from this line? What's an example of a point from this line? 0, 1. Great. So if I wanted to convert that point into a vector, how would I write that vector? 0, 1. So we can say my vector equation then is that. So how do we use this vector line equation to generate points? We're going to pick values for t, and those values for t are going to generate the points on our line. So for example, let's pick a value for t. 7. Okay. So over here, what type of multiplication is going on here between this vector and the number 7? Scalar multiplication. How do we do scalar multiplication? Good. The 7 is going to get multiplied to both components. And then when I add these two vectors, how do I add two vectors? We're going to multiply to add. We add the x's and add the y's. So this tells me then 14, 8 is a point on the line. Is everybody okay with that? So notice with these vector line equations, you're not picking an x-coordinate and finding a y-coordinate, right? Yeah. We're picking a value for t. T is just a parameter. It has nothing to do with the graph. Okay, it doesn't have any graphical representation. It's a parameter. So it's like a independent variable. So you pick a value for t, and what outputs from this equation is a point on the line. You get both an x and a y. Okay with that idea? Okay. All right. Okay. So let's say you wanted to find a possible vector line equation for y equals 3x plus 5. What is our slope in this situation? 3. So what should our slope vector be? 1, 3. You're correct. Okay. What's a point on this line? Okay, 0, 5. So what is our point vector going to be? 0, 5. Thank you. And so we're done, right? Notice here we said possible vector line equation. Why do we have that word possible? Could there be more than one answer, right? Could there be more than one answer to this? What if we picked a different point? What if, say, we had 3, 8, right? Then we'd get a different vector line equation. Does it matter which point we pick? Is that the only thing that can change? No. What else could change? No, the t is a parameter. That's just a variable. That's not going to be different in the equation. They're all going to have just a t in them. Is this the only way we could have written the slope? Couldn't I have written it this way also? Or 339 or whatever. So lots of different ways you could write that vector line equation. There's many possible correct answers. It does not matter to me which one you write. I usually go with the easiest route rather than making things more numerically complicated, but you know, you're welcome to do what you like. What if we want to go the reverse direction? What if we wanted to put this vector line equation back into slope-intercept form? So we need a slope and a point. What's the slope in this case? That is incorrect. You're looking at the wrong vector there, homeboy. It should be 3 over 2. The slope vector is the one attached to the t. Okay. And then what's a point from this line? 3, -1. Remember, x is on top, y is on bottom. So we can then say let's do -1 is equal to 3 over 2 times 3 plus b. Right? So that's going to give me -11 over 2 is equal to b. So we can just say y equals 3 over 2x minus 11 over 2. Sound good to you guys? Okay. So here's another Algebra 1 type question. We just want to find the intersection of these two lines. When we want to find the intersection of two lines, what are the different possible types of answers we get there? Well, how could the two lines intersect? There's 3 different ways that they could, or 3 different possible outcomes from this question. The obvious one is they could intersect at exactly 1 point, right? 2 points? No, not 2 exactly. They might not intersect at all if the 2 lines are parallel. And the third situation is where they intersect at infinitely many points, where the 2 lines are coinciding. They cannot intersect at exactly 2 points. Then it's not a line. Okay? So here is the idea on what we're going to do. So I'm going to rewrite vector R1 in its component form, or it's as a column vector. And I'm going to rewrite vector R2 as a column vector. And then what I'm going to do is I'm going to simplify these parts on the right-hand side. Is everybody okay with what I did there? Can we see that? What I did? Okay. So what I'm going to do then is I'm going to take these values for x, because I know x is equal to 2 plus s. And I also know that x is equal to -1 plus 3t. So I can set those two things equal to each other. And similarly, I know that y is equal to 4 plus 3s. And I know y is also equal to 5 plus 5t. So I can put those, or set those two things equal to each other. And what I'm going to do then is just rearrange these so that the variable stuffs are on one side and the constant stuff's on the other side. So that's going to give me 1s minus 3t is equal to -3. And then 3s minus 5t is equal to 1. And what I want to do is I want to solve this system of equations for s and t. So think back to your algebra class and tell me the fastest way to solve a system of equations. Well, that is a way to solve it. You could certainly do that. I would say there's a faster way that wouldn't require us to really write much of anything down. We can use our calculator. What are we going to use on our calculator? A matrix. Good. So let's review how to do that. So I'm going to open up my matrix menu. I'm going to go to the Edit tab. It's like the second and the third button down underneath the second button. And our matrix has two equations, so it needs to have two rows. And it has a spot for the s's, the spot for the t, and a spot for the answer, so it needs 3 columns. So I've made a 2 by 3 matrix. You go to the Edit tab, and then pick one of the matrices, and then you can just type in whatever you want. Nope, does not matter which matrix you use. So I did a 2 by 3 matrix, and then I just typed in the coefficients for my equation. So the first row is 1, -3, -3. The second row is 3, -5, +1. We okay with that? Yes. I'm going to exit out of my menu now, returning to the home screen. And then I'm going to go back into my matrix menu, but this time I'm going to the Math tab. And from the Math tab, I'm going to select the matrix command RREF. I went back to the matrix menu. I went to the Math tab and found the command RREF. It's way down there. Keep scrolling. And I'm going to do that RREF command on that matrix that I just made. You can do that if you'd like.
I got it right. I got it.
Oh my gosh.
Okay. So what does this tell us? This first row represents the equation 1s plus 0t equals 4.5, or just that s is 4.5. The second row says 0s plus 1t is equal to 2.5, or just that t is equal to 2.5. Is everybody okay with how to read that result from our calculator? So each row is just representing an equation. You just rewrite the equation with your s's and t's and equal signs and such, and it should tell you an answer. But this is not my point. My point that I'm looking for is an xy, not an st. How am I going to get an xy out of this? Plug what into what? Great. But in fact, rather than plugging them both in, I don't need to plug both of them in, because what I found is the value for s and t that gives us the same point. So I really just need to plug in either s or t into the correct equation. So for example, if I plugged s into this one, I get the point 17.5, 4.5. I hope not. Is everybody okay there? Okay. So these topics shouldn't be too bad, right? Very familiar. We're just doing things that we've done before in our algebra course, but using the language of vectors to do so. The last thing I want to talk about today is to begin talking about three-dimensional situation. We do. I'm not coming into work tomorrow because it's Saturday, but you're welcome to do that if you want to keep learning, but you're going to have to teach yourself. No, there's no school tomorrow. So what we're going to talk about today is mostly just some basic ideas for a three-dimensional space. So what I've drawn here is a three-dimensional coordinate system. So this dashed line you need to imagine as coming like out of the sheet of paper or out of the computer screen towards you and then back through the wall.
Yeah, I've already.
Let's make it simple.
This
Actually, pencil is paper.
Like a piece of paper.
that's what you're imagining. The dashed line is coming out in front of you because it's in three dimensions. Yeah.
Like this was the line.
Yeah. Okay. So this axis that's coming out of your sheet of paper is the x-axis. The one that's horizontal is the y, and the straight up and down is called the z.
Why did we make the y?
This is the traditional way that this is done. I don't know the origins of that, but this is the convention of how these axes are named. So let's say we wanted to graph the point 2, -3, 4. Okay. So to do that, I'm going to make 2 tick marks on the positive end of the x-axis. That's the part coming out of the wall towards you. Going to have 3 tick marks on the negative end of the y-axis, and then 4 tick marks on the positive end of the z-axis. Everybody okay there? I'm just going to plot this point. That's all we're trying to do. So I just need to make some scales. Yep. It's always, points are always listed in alphabetical order. All right. So what I'm going to do is I'm going to draw a line that is starting at the x, or the point 2, 0, 0, and I'm going to draw that line parallel to the y-axis. Okay. Then I'm going to take up the point starting at the point 0, -3, 0, and draw a line parallel to the x-axis. Is everybody okay there? What's your question? So I started at the point 2, 0, 0, and drew a line that's parallel to the y-axis. Then I started at the point 0, -3, 0, and drew a line that's parallel to the x-axis. Now I'm going to start at the intersection of those 2 lines and draw a line that's parallel to the z-axis. And where that z-axis line intersects that highest point on the z-axis, that is my point. Okay. So here is my, this side is my 2. This side is my -3, and that side is my 4. Is everybody okay there? You have to realize that you're looking at something in 3-dimensional space. It's not on a flat sheet of paper. You have to imagine it in 3-dimensional space. I know it's on 2-dimensional paper. It's on 2-dimensional paper. But imagine a perspective drawing in your art class. That's why I've drawn these lines that are parallel to the other axes. Okay. So if you're still uncertain about this, take a second look at the text pages. There's some good pictures that are better than I can draw by hand on the board of this process of what we're doing. And hopefully that should help a little bit. But it's mostly just getting used to kind of drawing this with a little bit of perspective. But that's why I'm drawing these parallel lines in to help me with the perspective.
So the point is like Is it like off the paper?
Yes.
Okay.
Yes. It's in front of your sheet of paper.
Is it like a cube to be like here on?
Yeah, so if you wanted to, you can think about this as like, there's like the bottom of my cube.
Yeah, that's what
There's the top.
Yeah.
There's a side. There's something coming back. You know, like one of these sorts of things. So there's something like that. Okay?
Why is the 2 down?
Because that's the part coming out of the sheet of paper is the positive part of the x-axis. This is the part coming out towards you. This is the part going back into the wall.
So negatives will be on top.
Yeah.
Well, how do you know how much like diagonal? Like the parallel with the.
Yep. Everything, you're just drawing stuff parallels. Okay? All right. So we have a distance formula for 3D. Remember the 2D distance formula? Looks like this, right? To turn it into the 3D distance formula, we just add a z part to it. So if you remember, for 2 dimensions, the midpoint formula is this. To turn it into the 3-dimensional version, we just do the same thing for the z component. Is that okay with everybody? Should be easy to remember. If you remember the 2-dimensional version, you can remember the 3-dimension because it's still the same thing going on, right? So let's say we have these 2 points and we want to find the distance in midpoint. Each of them? Well, a point there's no distance or midpoint for a point, right? You need a pair of points to calculate a distance between our midpoint. There's only a pair of points here. Because that's what a 3-dimensional point looks like. Okay. Everybody okay there? So that's just going to come out to be like 534 or something, or square root of 534. No, right? You're just using a formula. And there's our midpoint. Cool. That's it. So for your homework, what I'd like you guys to do is 51 to 75 odds.
That's a joke. There's more.
What? Oh, there's more. Oh, God. Why are we so